Okay, we have reached the second to last lecture, the quantum bound states. Until now, we have observed the striking difference between the classical Newtonian mechanics and wave mechanics. The wave mechanics explained the effect of photoelectric effect that light behaves like a particle, and light is the energy of that quantum, so-called photon, is determined by the frequency. The frequency and wave numbers determines are they are fundamental parameters that determines the wave nature. Hence, photon is a particle, and photon behaves the particle nature such as energy, momentum. They are all, on the other hand, determined by the wave parameters. So the theory was extended by applying relativity to the case of a more general case of Compton scattering, in which the binding energy of the electron to detach the electron from matter can be negligible. This is realized by introducing incident light wave with very short wavelength, such as X-rays or higher frequencies. In combination of wave mechanics and relativity, we were able to explain that the four momentum, the four vector representing the energy, relativistic energy and momentum of a particle, can be indeed used to explain the kinematics of that two-body collision. So now we would like to construct a theory, wave mechanics, based on these observations. In fact, we do not have to throw everything away, but we had better change our basic assumption, and the derivation of the derived quantities, useful physical quantities, are the consequence of that very simple assumption, so-called postulate. For example, if we study relativity, we didn't introduce many parameters to explain the experimental results. The only two assumptions we have introduced was, the first of all, the speed of light is constant for any observers. That is the experimental result obtained by Michelson and Molden. The second one is simpler, perhaps simplest. Any physics law must be described in a consistent way for any observer standing at a frame of reference that is called inertia, where the law of inertia is working. Now, we would like to implement the wave nature into particle kinematics and dynamics. However, such kind of behavior can be observed directly from the Newtonian mechanics. The musical sound of instrument has a specific resonances that is exactly the same as the quantum nature of wave mechanics. This is the reason why I'd like to talk about the vibration of a string, violin string, guitar string, their vibration, their resonance frequencies are quantized. Sure, there are many other frequencies that can vibrate the strings. However, because of the damping effect, all the other frequencies except for such fundamental frequency and fundamental harmonics and its multiples, any other frequencies will decay and we could not notice the other frequencies. If we carry out purely Newtonian approach to analyze the motion of a vibrating string, we end up with the fact that that everybody knows the string sound is quantized, but they never use the quantum physics when they hear that sound. But actually, that is hidden in the sound nature. In addition, if you look at the flag, that generates a wave, and we can see the frequency and wavelength. That is also the same nature, that has the same nature as the vibrating string. That's the more general case called the membrane vibration, and that is also related to the vibration of drum and so on. So our starting point today is coupled oscillator. Coupled oscillator is just a connected oscillators. We remember that a simple harmonic oscillator has its own characteristic frequency. Its angular frequency omega is square root k over m. If the spring constant is increases, then the frequency of oscillation increases. If we increase the mass attached to the spring, then the characteristic frequency decreases. Anyway, a simple case is to connect identical simple harmonic oscillator. We have a spring and the other spring, they are identical. And I'd like to introduce a weak coupling. Weak coupling means the spring constant of the spring that connects the two masses is rather smaller than the other two original one. If we break this bondage, what happens? These two oscillators oscillates with the same frequency of a original characteristic frequency. However, if we introduce the connection, then they talk to each other. And for example, let me just leave this oscillator as it is and just to shift this mass a little bit and release. What really happens is it's oscillating at first, and then the weak coupling transfers energy, and at someday this oscillation is shifted to the right and the left side becomes calm and back and forth. This is a real nature of coupled oscillator. Anyway, first, if there is a weak coupling, we have original frequency that has a standard frequency, but we we observe there is another time scale that is much bigger than the period of original oscillation. That is energy transfer, slow energy transfer to shift the whole system to be, for example, in the initial state, this was fastly oscillating, right side was calm, and then at some time later, the 10 or 20 times of oscillation of each oscillator, they are flipped. The situation is flipped. And then additional 10 more oscillations, the left one is busy and right one is idle, and so on. That means there are two time scales. The first time scale is determined by the original oscillator's frequency, inverse of that frequency, and there's another time scale that is much longer than this that is introduced by this weak coupling. Because there are two independent time scales, inverse introduces two different frequencies, that means normal frequencies. Mathematically, we will find that these frequency carries a relative amplitude of the two oscillators. They are called eigenvectors, characteristic vectors, something like that. A single simple harmonic oscillator has a single characteristic frequency that is also called eigenvalue, frequency eigenvalue. And it had only a single amplitude. The eigenvector is just number one multiplied by time dependent factor, that is sine or either sine or cosine omega 0 t. And if the linear combination reaches the single sinusoidal function with omega 0 t plus delta, something like that, shifting the phase. Okay, let us look into the equation of motion for these coupled oscillators. I have two masses placed at x1 and x2, and these two coordinates are chosen to be 0, where they are at the equilibrium position. And Newton's law of motion says acceleration of the first object is determined by the force applied to this object, and the force due to this spring and this spring combine together to construct the equation of motion. And this coordinate x1 appears in here because if we ignore the weak coupling, and contribution of the weak coupling is the one here. Now we, in order to further simplify the problem, we have just chosen the identical spring constant. All three spring constants are equal to k. In that case, I can use the same spring constant, and the displacement from the equilibrium position is proportional to x1, but we have to subtract the relative position, the x2, because the modification of the original length depends on x1 minus x2. In a similar manner, we can construct the equation of motion for the second mass. And the equation of motion is identical to the first one, except that we exchanged 1 and 2. If we simplify, move everything on the left hand side and divide the equation by the common mass m, then we end up with a simple linear equation, that is a second order linear differential equation. I have constructed a vector, two-dimensional vector, whose components are the coordinate of the first mass and second mass. And then there's a matrix coming out of these coefficients of this x1 and x2, and this is the system of linear differential equations. Just like what we have done with the Schrödinger equation, we we find that operator of the Schrödinger equation is second order second order derivative with respect to the spatial components, and a single time derivative that represents IH bar and minus H bar square over 2m del square. These two operators appear in the partial differential equation. However, they are not multiplied, they are not mixed at all, and they are just a simple sum, linear combination, and the coefficients are independent of either coordinates or time. That's the reason why we can solve this equation as by applying separation of variables. Wave function is actually function of time, both the time and spatial coordinates, but you are able to rewrite this one as a factor that contains the spatial components only and multiplied by the function of time only. And then we have constructed equation for the psi x that depends only on x and tt that depends only on t. Using this relation, we were able to solve the equation for psi and t separately. And t solution for t is a trivial solution, and solution for psi is the time-independent Schrödinger equation. And actually, that really works in this problem too. The spatial components are separated into two components of this vector, and we introduced the separation of variable for these elements for the entries of the vectors, and then we assume that the time dependent vector is completely factored out. Simple way to solve this problem is we introduce a trial solution for the time dependent part, just like what you have done with the time dependent Schrödinger equation, because it is a in if we introduce a single component, this one reduces into the simple harmonic oscillator. And simple harmonic oscillator second order linear differential equation can be solved by substituting the exponential function. And it's fine, we can either substitute e to the lambda t, but we at the end of the day we will find that lambda should be purely a pure imaginary number. Anyway, the separation of variable for the solution for this two component elements that are depending on time, we substitute this one. Then the second order derivative is just omega squared minus omega squared. That's it. And a is, because a vector is independent time, the second order time derivative of x is simply this one. Finally, the time derivative can be replaced with a variable omega squared that is not determined yet. And as a result, in just like the time independent Schrodinger equation, we are left with the linear equation to solve that is called the eigenvalue equation. While omega 0 is fixed for each oscillator, if we have multiple oscillators coupled together, then we have a variable oscillation, variable frequency. And that variable frequency, we shall find that these variable frequencies are not continuous, but they have some discrete values. The solution of this equation is the eigenvalue equation can be solved uh, in a various way, and usual way is to solve in determinant equation using the fact that the if A is non-trivial, that means A is not a simply zero vector. Zero vector is called the trivial solution. If it is not the case, mathematically, the determinant of this matrix must be zero. If it is not the case, the matrix has an inverse. If we multiply the inverse, then we end up with A minus lambda I inverse A, inverse 0, because right side is 0. So we end up with A equals 0 vector. But we are not interested in such a trivial solution. So according to reduction to absurdity, it is not the case. Therefore, determinant of this one is a 0. Determined for n by n matrix, this determinant is always a polynomial of lambda, polynomial in lambda of degree n by n case. Because we have 2 by 2 cases, it is quadratic equation. So if we solve this quadratic equation, then we find two values for lambda. If we find two values of lambda, then we make use of this and determine the eigenvalue, eigenfrequency. So new characteristic frequency for the coupled oscillator are determined to be two values. A very simple way to solve this kind of problem is recently introduced by Kpop Collaboration, and you might be interested in reading it. As we can see, we have indeed two different frequencies. Sometimes when we solve quadratic equation, for example, x squared equals x squared is 0, then what happens? X is 0 only, and actually they are 0 and 0. The quadratic equation must have two different solutions, but the happen to it accidentally the two solutions become the same when the discriminant of the quadratic equation vanishes. You say when all of these characteristic frequencies are distinct, then we say non-degenerate. Non-degenerate. And if some of them are equal, then number of distinct characteristic frequencies are less than the degree of the linear equation, that equation, polynomial equation. In that case, we say they are degenerate. All right, so Having found that there are two characteristic frequencies for the coupled oscillators, we extend this idea to the case of n-coupled oscillators. Simplest case is the vibrating string. In the last semester, you have learned the wave equation for the vibrating string. Well, this one can be solved very formally. Let me tell you how to solve, but it's, we do not have enough time to explain every detail of the derivation. The simplest way to consider is vibrating string can be thought as a connection of tiny parts, and each part has its own mass, very tiny. So we can make an approximation that small masses are distributed all uniformly all over the string, and they are connected with the string that has elasticity. Okay, and in fact, we cannot separate, but we can think about the separation of masses, and then their connection is elastic wires, elastic strings. Then it becomes a set of oscillators of n masses. We choose n identical beads of mass m, and the distance between any two adjacent beads is d, small d. And place, we allocate the integer k. The first one is 0, and the last one on the right wall is k equals n. If there are n these, it's better to choose n plus 1 because this one is k equals 1, 2, 3, 4, and n. Okay? ID 1 and ID n. And the left word is ID 0, and the right word is ID n plus 1, something like that. Let us choose the ith beat somewhere. And if we consider the motion of this a single bead, the equation of motion will be mass times acceleration, and we just consider the transverse motion of the bead, and actually there are two. If this is x-axis, we have y and z axis, but for simplicity we just ignore this z direction, and this bead let us vibrate this bead along the y direction only. In that case, the problem is simplified, and we consider the tension of the string is constant, almost constant. That means the vibration is not very much significant, and this vibration is a tiny vibration. All right, so when it vibrates, the string makes a curvature, and an ith beat has some angle. The string attached to the ith beat has some slope, I plus 1, and I minus 1. where I runs from 1 to all through n. Okay, then let me call this angle to be theta 1, the angle with respect angle between the horizontal line and line connects the ith and I plus 1 bead, and let this one is theta 1 and theta 2 be the angle between the horizontal line and the left nearest object. If it is in this shape, is going up, the force on the right side is going up and force on the left side is going down. So there is a sign difference. This sine theta is actually calculable if the distance, if this spacing is d, and there is a difference in the transverse coordinate, this yi and yi plus 1. That means this side is y I plus 1 minus yi. And this part, this length, right? This length is yi minus yi minus 1. We have substituted this result in here to find this equation. M is divided, and we have factor out the tension over the factor as a tension, and we have difference divided by this spacing, difference divided by this spacing. We notice that this one is actually the derivative of y with respect to x. This is x direction, proportional to, in the limit as v goes to 0. And derivative is subtracted. So this part, right derivative and left derivative, their difference. If we divide this one by d one more time, then we find that this is a second order derivative with respect to x. In addition, second order time derivative can be expressed like that. And just like what I have told you, the right hand side is related to second order derivative with respect to spatial coordinate. Finally, if we combine these two, we end up with the equation that is the wave equation, and velocity of the propagation of the wave is determined by this one, square root tau over mu, where mu is the mass density. Mass density means the m over d. If you want to solve this problem, you can follow these steps, and uh, our recent paper explains in detail. It's much better than the usual derivation given in the normal textbooks. Anyway, at the end of the day, you will find that eigenvector, that means a vector, a vector, a vector. A vector is a constant vector that is independent of time. We recall the solution is the a vector multiplied by e to the I omega t minus I omega t, something like that. But actually, the imaginary part does not exist at all in the real space, in the Euclidean space, in XYZ space. So at the end of the day, you will find that because of the boundary condition that the string is fixed on both sides of the wall, linear combination e to the I omega t and e to the minus I omega t, a plus b, this kind of style is can always be expressed as a sine omega t plus b prime cosine omega t. Okay, and in the spatial part, it is we can replace this t by x. We will find that this sine kx, cosine kx, c prime d prime, this kind of form. And when we substitute x equals 0, this one must vanish. When we substitute x equals L, if it is the length of the string is capital L, this one also vanishes because of this boundary condition. String vibration is always a standing wave that has a form of a sine kx, but this kx is determined. This wave number is completely determined. How? Like this. This one shows that our we learned in the previous semester and even high school the string vibration even in mathematics class without learning this detailed calculation. We just consider the continuum limit as n goes to infinity and the d goes to 0 and mass density is finite. In that limit we took it for granted that string vibration has the fundamental resonance, and this is the n equals 1. This is fundamental harmonic, and this first excited states, and then and so on. This kind of solution is absolutely derived from even the finite combination of vibrating string. I mean, the finite number of beads connected by elastic strings, they also have this kind of form. And the frequency of oscillation is completely determined as integral values. When we learn interference of waves, I have introduced it from the beginning to study phasor as generally as possible, and you already have proved this summation relation. It can be solved by using the geometric series of complex number, and in addition it can be solved using some residue theory that is introduced in our Kpop collaboration paper. Anyway, the solution can be generalized to a continuum limit as n goes to infinity and m over d equals to mu is a finite. In that case, it is indeed a vibrating string. And the solution is sine wave. And this is an eigenvector that represents relative coordinates of this all particles from x runs from 0 to L. There's a left hand and right hand. They are showing the sine shape. And the wave number is s pi over L, and s runs from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, until not infinity, but to the n, where n is the number of bees. Because we take the limit n goes to infinity, there is no upper bound, and it will go through infinity. So actual vibration mode is composed of fundamental frequency, that is the wave number, pi over L, and then it becomes 2 pi over L and 3 pi over L. This is what it is, K. K is 2 pi over lambda, right? Wave number. is increasing as a step by step. So wave number is quantized. Even in classical mechanics, wave number is quantized if we have a specific boundary conditions. So quantum mechanics, quantized energy level of quantum mechanics is not really new. We have already knew such kind of quantized states in classical mechanics, Newtonian mechanics already, but we didn't generalize this idea to the quantum mechanics at by that time. Okay, let us extend this idea, generalize this idea to understand the quantum bound states. Just like the vibration of a loaded string with fixed ends, quantum state bounded by some force is always quantized. If it is not quantized, we say it is continuum. Vibrating string attached to two words has the boundary condition at x, this if we choose this x-axis and coordinates to be 0 and L, then vibrating string has a wave number determined by this kind of standing wave, and we have additional time dependence. This is a standing wave vibrating up and down, and its a frequency increases as the wave number increases, and so on. So hydrogen atom, we have proton, and there's attraction due to the Coulomb force. So electron is bounded, they are quantized. In a similar manner as the vibrating string, an electron is trapped in a box. It is oscillating. Inside, the wave function that represent the all of the dynamics nature of the particle is determined by the wave number, and wave number determines the frequency of oscillation. This is also bounded. As a result, its momentum and energies are quantized. It has discrete values. It does not have any continuum value. But as soon as we break this bondage and we remove this wall, then there is no limitation of having quantized energy or quantized momentum. Free particle has e to the I kx minus omega t. This k is not restricted to a quantized number. It is called the continuum. So, in this chapter, we restrict ourselves to the bounded particles in wave mechanics, resulting in quantized states. We recall the wavelengths of this wave property of the particle is determined by de Broglie wavelength, and lambda is Planck constant over momentum. We recall that this momentum is not restricted to the non-relativistic theory because it came From the fully relativistic theory, this momentum is a relativistic momentum. And in the limit, as v goes to 0 in comparison with the speed of light, it is this p can be treated as mv, where m is the rest mass. If it is fully relativistic, it should be considered, this m should be considered as a rest mass over 1 minus v squared over c squared. Once we know the wave number, wave number k is p over h bar, or 2 pi over lambda. Once you know the wave number, we can determine the momentum with this de Broglie wavelength and h over lambda, and using the notation for wave number, h over lambda can be expressed as h over 2 pi and 2 pi over lambda, and this is reduced Planck constant and this wave number. That is linear moment. In non-relativistic theory, the kinetic energy will be like that. Sure, if you consider relativity, kinetic energy is m0c squared gamma minus 1. And if you add the rest mass, rest energy due to the rest mass, then this rest mass term cancels, and kinetic, the net energy, total energy, that is the sum of rest energy plus kinetic energy without the presence of any other potential, is mc squared multiplied by gamma. That is m0c squared divided by 1 minus v squared over c squared. So kinetic energy is like that. In the free particle case, potential energy is 0. Kinetic energy is total mechanical energy itself, and that is kinetic energy is total mechanical energy. Momentum can be read off from the energy because of this relation. P equals to me p squared, and P equals plus minus 2me in the single directional motion. So plus minus means if it is moving to the right or either right or left. Using this, we can determine the wavelength as it is. Wave number is also determined in a similar manner. So in one dimension, free particle is either it has the spatial component that has e to the ikx that is moving forward, and e to the minus ikx that is moving backward, and that wave number is completely determined by the total mechanical energy, that is kinetic energy. The big difference between the classical wave equation that describes the vibrating string and the Schrödinger equation that describes the wave mechanics of a particle is this. This is a classical wave describing the vibrating string, and Schrödinger equation as far as the spatial derivatives is concerned, it is very similar. However, time derivative, we have double time derivative for the equation of motion for a classical wave. describing the vibration of string or membrane. However, in the case of Schrödinger equation, what we have is actually the Hamiltonian. It just the read of the energy itself. So that is the difference. In classical theory, all of the coordinates are real because we directly measure all of that. Sure, if we consider the electromagnetic wave, it can be generalized to the complex phase. But in quantum theory, what we write is not directly wave equation, but we have Hamiltonian is kinetic energy plus potential energy. So we mixed this one with the plane wave solution for e to the I kx minus omega t. This plus this generates yields Schrödinger equation. So it one this left hand side has a single derivative with respect to time. As a result, psi is always we can always construct a solution for this wave equation in a real form. In general, the solution for this Schrödinger equation always include a complex number in general. In a specific case, the complex phase can be completely factored down so we can we can make an approximation that not an approximation. We can always find the basis in which in some problem we can describe the wave function in a real valued function. However, that is not in general. So because of this second order derivative appearing in the wave equation and the first order derivative appearing in the Schrödinger equation. So let us recall how to construct the Schrödinger equation for the quantum mechanical wave equation. We first introduce the free particle solution. That is, a free particle means a plane wave. Plane wave means that the momentum is fixed. Momentum is fixed, then the wave number is fixed. If the wave number is fixed, then the wavelength is fixed. Plane wave propagating along a single direction. Lambda is fixed, then k is fixed. Once k is fixed, then multiplying k by h bar, momentum is fixed, it is a constant, momentum does not change. Then this is a free particle because this is zero. So if we take the time derivative, what we get is h bar omega, that is the energy. If we want to find the momentum, what we can do is h bar over I gradient. Take an operation to this free particle wave function, what we would get is psi, then what we would get is a p momentum p vector multiplied by psi. If the free particle is a photon, energy is to be replaced with h nu and put 2 pi below and 2 pi nu is h bar omega. And mass share condition can be used to find the momentum of a photon, can be obtained by substituting the rest mass m equals 0. Then energy is Pc proportional to the free moment, the magnitude of the free moment. For elementary particles satisfying the governed by the wave mechanics, if the velocity is much smaller than the speed of light, then we can make an approximation of a non-relativistic limit. In that case, we have a rest energy plus kinetic energy. In fact, real kinetic energy mc squared gamma minus 1 if we used m as the rest mass of the particle. Finally, if we either relativistic or non-relativistic, what we find, the free particle wave function kx minus omega t is k dot x minus omega t equals, if I multiply h bar, so I pull out one of h bar and into h bar k minus h bar omega t, h bar dot x. That means 1 over h bar and p dot x minus et. Then actually we can rewrite this one in e over c and ct. If I keep all of the vector I, this is I, this is I, and then at the end of the day, if we exchange the order, that is e over c x0 minus p dot x. What's that? This is a scalar product. P and x, they are four vectors, for momentum and for displacement. That means the free particle wave function, it looks non-relativistic. However, it is completely relativistic, and its free particle wave function is, this one is Lorentz scalar, and exponential of a Lorentz scalar is another Lorentz scalar. So this free particle wave function, exponential minus I over h bar p dot x. This is Lorentz invariant, Lorentz invariant scalar invariant under any Lorentz transformation, and it's invariant. This is just like the speed of light. This is the same for any observer placed in any inertial reference frame. The reason is that de Broglie wavelength is defined based on the completely relativistic theory instead of non-relativistic theory. Okay. As the simplest bound system, we consider infinite potential well. In classical mechanics, if there is a potential barrier, an object is inside, it can travel, the particle can travel inside. If the motion depends on the energy level of the particle, if a particle has the energy, this plot is for potential energy. In classical mechanics, Newtonian mechanics, energy, total mechanical energy is the sum of the kinetic energy plus the potential energy. Kinetic energy is the p squared over 2m, and all variables are real, therefore is a positive definite. Sure, if it is at rest, it becomes zero. Therefore, energy subtracted by the potential energy is kinetic energy. So energy must always be greater than the potential energy. At this boundary, energy, the potential here is above the total mechanical energy. Therefore, it is impossible to penetrate the wall. That means there is a turning point. Any any potential any potential energy given and a particle energy is fixed, that is conserved under the conservative force. Motion is oscillating in this region because and a total mechanical energy cannot be greater than the potential energy. So we say these are turning points. So it is impossible to penetrate the potential wall that is above the total mechanical energy. That means the kinetic energy is positive definite. Let's see what happens in the quantum mechanical case. The simplest case, we introduce a potential wall. The wall is infinite, can never pass it through. And consider, then this is an infinite wall. So we have a well. The potential energy U of x is drawn like that, for x is here at 0 and L. We say potential energy is 0. And except that outside that region, potential energy is infinite. So this is the way to hold an object inside the well. We want to find out the solution for the wave equation that is called the Schrödinger equation. And time dependent Schrödinger equation can always be factored into the wave function of the time dependent one, can always be factors if we consider a single energy level. So introducing the energy eigenvalue of the system, which is unknown temporarily, and oscillation time dependent oscillation factor is always in this form because time dependent part must satisfy the psi t x is psi x multiplied time t. Then it is written in the form, it is energy, that is h nu, and that is also the same as h bar omega t. Then because of this, the relation becomes E psi equals kinetic energy in the one-dimensional motion, like that. We have the potential energy inside vanishing. In the region, x is between 0 and L. Because there is a discontinuity, so it's better to use less than, instead of including 0. So in the region between x x equals 0 and x equals L, it is simply free particle. Free particle, this relation can be simplified in this form. Let's say because energy is not a function of position, energy is just a number. This, this is the one that is a number. In addition, the potential is here. There are three possibilities. Energy is above the potential, same as the potential, and below the potential. In the questions, we will consider this problem in a rigorous way. That you will find that the wave function, discontinuity of the wave function, especially at the point of discontinuity in the potential energy, will be considered. Right now, we just simply consider the positive energy case. There is of no use to consider the case that energy is at zero. If energy is zero, then means momentum is zero, because the kinetic energy to be zero, that means a wave number is zero. If wave number is zero, then there's no oscillation at all. The wave function is of the form sine. This kind of form, if I substitute n equals zero, the wave function itself is zero when n equals zero. If wave function is zero, then wave function squared is the density of the probability density of finding the particle, but that is zero. So the particle, that state is does not exist at all. So the wave number, the momentum, zero, that kind of thing does not contribute in, does not make sense in the physical contribution. So there are two possibilities. Energy is a positive or either positive or negative. If it is positive, it, the solution looks like the harmonic oscillator. Harmonic oscillator is x double dot plus omega 0 squared x equals 0. Omega 0 squared is always a positive definite. Then the solution is a sine omega 0 t and cosine omega 0 t up to over constant factor. The linear combination of this will be the solution. Now, this psi, the derivative is not with respect to time, but with respect to x, and there's some, let's say omega 0, why not for omega 0 squared, psi equal 0. We just replace this one with psi of x equals sine omega 0 x instead of t, and cosine omega 0 x, and c1, c2. That is the solution where omega 0 is, what's that? Let's go to 2me over h bar. Now it's better to not to use omega because it's not a time derivative. This is omega. This is wave number k. K squared. So sine kx, cosine kx. This is the way to solve this problem. Another possibility is that energy is negative. If energy is negative, it is not a sinusoidal function, it's not an oscillating function, but an exponential function. Something like this kind of exponential function. it should decay as it goes to the right, and it should also decay when you go to the left because the potential is above the energy. In classical Newtonian mechanics, the energy must be below the potential energy, but in quantum mechanics, it is allowed. Instead, as we have studied for the damped harmonic oscillator, in certain range of damping term, the oscillation exists, or, for example, underdamped case. For underdamped case, it is oscillating, still oscillating, even though there is a damping factor, a damping term. However, if the damping coefficient increases and arrive at the threshold where the critical damping exists, and after that, the oscillation, there is no oscillation anymore, and the solution becomes exponential. It is unphysical to have the exponential growth as the time goes because the energy should decrease because of damping. In such a manner, when the energy is below the potential, the oscillating behavior stops and the probability, the wave function, decreases exponentially. And in the limit, very much outside, it will decay and finally the wave function must vanish in this region. So anyway, uh, that's for your study of questions. So let me concentrate on the free particle state in between the walls, and you'd like to find the solution to be vanishing at the end point. That you should prove in the questions. And the wave function must be continuous. That is another problem you have to solve. But for example, there's a rigid wall in classical mechanics. A ball hits the wall, and right after it meets the rigid wall, it bounces back. What we observe is before there is a t equals 0 and t equals negative, t equals a positive. When t equals negative, momentum was a positive. And right after the bouncing, the momentum becomes negative. So there is indeed the singularity, the discontinuity in the velocity and momentum. However, this is actually due to the elastic collision. Suppose that there is some spring is in it. Spring is inside, uh, is attached to the ball. Then it slows down and returns. If the K is very large enough, we do not notice the amount of oscillation. It looks abruptly, it bounces back in a very, very short time. Anyway, during this discontinuity of momentum, we must keep in mind the total mechanical energy never decrease or never increases, even though because there is no driving force and no damping is assumed. Therefore, momentum and wave number, that the momentum may have the discontinuity. The wave function does not have discontinuity. The reason is that the wave equation has a second order derivative. The first order derivative is related to the momentum. And if you integrate the second order derivative about that point of singular the discontinuity, you will reach the value of momentum. And that's the hint. There is a discontinuity in momentum. However, the energy must be conserved in the system of conservative force. If you require that kind of restriction, then you will find that wave function is continuous. Therefore, inside it is a linear combination of sine kx and cosine kx. And this wave function must be continuous at these 2 points. And wave function must vanish outside. Because at outside it is either exponential of this one or this one, something like that. And they must vanish at the plus minus infinities. Therefore, outside wave function must vanish. Inside sine, linear combination of sine and cosine, and wave function must be continuous everywhere. So it must be continuous at the boundaries. The only solution that satisfies all these restrictions will be sine of this. That is exactly the same as the normal modes of vibrating string. And we already have computed that these wave functions are orthogonal based on the summation relation for there should be an identity of a product of signs with different integer indices. So using this, we extended our previous result for the normal modes of vibration to generalize it to solve the solution for a particle trapped in an infinite potential well. And infinite potential well provides a discrete energy level whose momentum is completely fixed to either plus or minus with multiples of this simple vector. And energy level is complete depending on that quantum number n, and and quantum state n equals 0 does not exist because the wave function itself vanishes when we substitute n equals 0. The average value of the energy of the interference superposition of all possible states will be the energy level that is proportional to the n squared weighted by the probability density. That probability, each state's probability is determined by this coefficient complex number. So such kind of state, if such kind of state exists, then the transition of the state will result in the emission of a photon with h nu or h bar omega, and that is proportional to the difference of square of integers. It's a little bit different from the transition for the hydrogen atom that has integer 1 over integer square difference. Okay, so this is a simple example of finding that the bound state of wave satisfying the wave mechanics, satisfying the Schrödinger equation, is always quantized. Okay, we will extend this idea to the hydrogen atom in the next chapter. That's it for today.